Chapter 3. Another tool of science. Measuring. Quote, measure what is measurable and make measurable what is not so. Galileo Galilei. In this one sentence, Galileo summarized the scientific pursuit of the 16th century. His words remain relevant today, capturing the essence of our ongoing quest to quantify and understand the world. While technological advancements have enabled us to create more precise measuring instruments, the journey to make the unmeasurable measurable continues. Many phenomena that were unmeasurable in Galileo's time remain elusive today. For example, despite significant scientific efforts, measuring happiness accurately and precisely is still challenging. We will discuss the science of happiness in Chapter 16. In this chapter, we will first define measuring. After that, we will discuss science's challenges in making the unmeasurable measurable. So, what is measuring? In its simplest terms, measuring is the act of denoting when an object or phenomenon stands against a standard and widely agreed upon model. For instance, when measuring the height of an individual, we denote their height against the standard metric system. The standard metric system is a model of length. Please pay close attention to the word model. It is what we covered in the previous chapter. As another example, when measuring the amount of rainfall, we use a standard instrument of measurement, a circular funnel with a diameter of 203 millimeters that collects rainfall. We get a rainfall measurement based on how much water is collected. Scientists must ensure their measure is reproducible when developing new measurement instruments and models. This is the most fundamental characteristic that a decent measurement model needs to possess. A reproducible measurement standard can be repeated in all parts of the world, and the results should be the same. To understand the idea of reproducibility, let us explore the history of time measurement. Over the years, various instruments and models have been developed to measure time with increasing precision and reproducibility. One of the earliest precise timekeeping instruments was the water clock, clepsydra, which functions similarly to a sand clock but uses water to mark the passage of time. The consistency in water flow allowed for relatively reproducible time measurement. However, as technology advanced, more precise instruments like mechanical clocks and eventually atomic clocks were developed, providing even greater precision and reproducibility in timekeeping. The reproducibility of these water clocks depended on various factors, such as the size of the hole that the water drips through, the amount and quality of water used, and the age of water clock itself. Continuous use of a water clock could lead to erosion of the surfaces, causing larger holes and allowing more water to pass through, thus affecting the precision. Additionally, the consistency of turning the clock at the exact moment when the upper container is empty is crucial. The kings and queens of the ancient times could afford to task a group of people to observe the water clock, turn it around conscientiously, and denote the passage of time. Still, even that could not be very reproducible. So if a queen would get mad at her date for not being on time, she may have needed a copy of my book. Today, we have made such strides in creating reproducible measurements that we have more grounds for being upset when our date is even a few minutes late. It is now safe to assume everyone can access highly precise and reproducible timekeeping instruments. The way we ensure that our time is reproducible is mind-blowingly impressive. The International System of Measurement for a second is defined as 9,192,631,770 periods of radiation corresponding to the transition between the two hyperfine levels of the ground state of the cesium-133 atom. Although we do not require such precision in our daily lives, atomic clocks, which offer precision to the millionth of a second, are now available for about $1,000. The second characteristic of a reliable measurement instrument is that we know the extent of its error. For instance, with atomic clocks, modern technology allows precision to the billionth of a second. meaning the reported 1 second might be between 1.000000001 and 0.999999999 seconds. Despite all technological advancement, complete precision remains unattainable. And that's the fundamental reality. We will never achieve absolute precision. That takes us back to the backbone of science, modeling, which we discovered as the first method of science in the previous chapter. Any measurement model, system, or instrument is essentially a model or a combination of models. In the case of time, as we know and use it, two models work in concert. The first model assumes that a day, the time it takes for the Earth to complete one rotation, consists of 86,400 seconds. This number comes from multiplying 24 hours by 60 minutes and 60 seconds. The second model assumes that the period of cesium radiation remains constant. This is an assumption because we lack the instrument to measure and verify it. Our most precise measurement instrument is based on this fundamental assumption. With simple calculations, we might expect that a day, the time it takes for the Earth to complete its rotation, would last exactly 86,400 multiplied by 9,192,631,770 cesium radiation periods. And drum roll, please, that is not the case. The time it takes for the Earth to complete its rotation is inconsistent year over year. The Earth has been gradually slowing down. This discrepancy highlights the complexities and challenges in creating precise and reproducible measurement models and devices. As what we know as a day depends on the rotation of the Earth rather than the number of cesium radiations, we need to have these two models connected with regular correction. Since 1961, we have been using these two models in concert under Coordinated Universal Time, UTC. UTC uses two times. The first is universal time, which reflects our best effort to measure the actual length of a day on Earth. It is calculated by measuring the pace of the Earth against the most accurate atomic clocks. The second one is known as International Atomic Time, TAI. TAI is the average time measured by 400 highly precise atomic clocks worldwide. UTC, the time we see on our cell phones, is a compromise between UT and TAI. The mechanism is that whenever the difference between UT and TAI approaches 0.9 seconds, a leap second is added to UTC. The last leap second was added in December 2016 by the International Earth Rotation and Reference Systems Service. When we dare to look under the hood of these models, systems, and agreements, scientists have dealt with a lot of messiness for us, and we get to use the fruit of their work. What is the fruit of their work? An accurate and precise enough model of time. If you have a keen eye, you may have noticed that I used two adjectives in the last sentence: accurate and precise. What purpose do these adjectives serve? Do they contribute meaningfully and differently to the sentence? The answer is yes, based on their scientific definition. Even though everyday English uses these adjectives interchangeably, they have distinct scientific definition and usages. According to the correct usage of these words, we can call a model accurate or inaccurate, but not precise or imprecise. On the other hand, we can call a measurement precise or imprecise, but not accurate or inaccurate. Let us look at two extreme examples to understand the scientific meaning of accuracy and precision. We will first look at a combination of a model and measurement that is inaccurate but precise. Let us say I managed to travel back in time and smuggle with me an atomic clock. As ambitious as I have always been, I want to raise my status quickly, even during my travel back in time. So naturally, I will directly go to the city's king and try to give them the good news that I have brought them the gift of time. After I spent a few days in a dark prison, what did I expect? The king to name me his heir in our first meeting? The king came to tell me that he was amazed at my magical device and how it seemed to show similar changes during one cycle of his best water clock. That will be enough for the king to trust me and ask me to help him share the gift of time with his people. So I get to work. First, I will order them to create a tall building with a big bell on top so everyone in the city can hear its chiming. Then I start scratching my head because I have no idea how to measure when the Earth finishes or starts its rotation. I should have studied my horology better before my time travel. I hope I can go home alive. Hastily, I decide to use sunrise as a proxy for the Earth starting and ending its rotation. Phew, thank God I'm a genius. So, I asked the king for one soldier to help me with the project and ordered the soldier to start the clock when the sun rises. Once the clock shows the hour, the soldier will ring the bell for each corresponding hour. Once for 1 o'clock, twice for 2 o'clock, and so on. I also instruct the soldier to stop the clock and go home when the sun sets. With this system, in a matter of few weeks, I became the city's hero because now everyone can plan and have access to a reliable time. People have come up with the term hours after sunrise. For instance, as I set my date with the most beautiful girl in town, thanks to my newly earned fame, we agreed to meet 7 hours after sunrise. Within a few months, my fame and newfound powers have gone to my head, and I become a drunken slob. Around that time, everyone started noticing that daily hours were declining. While there were 14 hours in the beginning, it is now around 11. The word gets out that I am a fraud and my time is not accurate enough for people to rely on. The king orders me to be captured and imprisoned again. While I await my sad execution, I realize my mistake. Even though I had a very precise device to measure time, my model of the day based on the sunrise needed to be more accurate. Due to the Earth's axial tilt of 23 degrees, the length of the day changes. And by relying on sunrise and sunset to model the day, I should have warned everyone that there would be more hours during the summer than during the winter. My measurement device was precise, but my model was inaccurate. This imaginary travel back in time is an example of an inaccurate model but a precise measurement device. Let us consider an example of an accurate model but imprecise measurement. The other day, I wanted to purchase a rug to spread under my dining table. Before going to the market, I needed to find a way to buy a carpet that was the right size for my dining table and dining room. Being the inventive kid that I am, I drew a rectangle on a piece of paper as a model for the rug I needed to buy. To measure the size of the sides of the rectangle, I went into the dining room and counted my steps, walking the sides from one edge to another. Then I wrote the number of steps as the measure for the size of each side. I took the piece of paper to a nearby rug store to see if I could find something suitable. After walking around the store and finding a few lovely rugs for my dining room, I asked a store attendant to help me find the right size. When I showed her my piece of paper with my measurement, she wondered in what units the numbers next to each side of the rectangle were. I said, "My steps," defiantly. "Steps are not precise enough, sir," she sneered. In this story, my model was accurate enough, but my measurement, as the store attendant said, was not precise enough. I used a rectangle to model the rug. The reduction level of this model was acceptable. In other words, the model was accurate enough. However, the measurement I used was not reproducible. How did I expect a store attendant to use my steps to give me the rug I needed? With the rug story, my goal was for you to see an example of an accurate enough model but imprecise measurement. Alongside my imaginary time travel story, which had the other extreme of an inaccurate model but a precise measurement, we are better positioned to understand the difference between accuracy and precision. To correctly use the term accuracy, we must ensure we are talking about a model, not a measurement device. On the other hand, to use the term precision correctly, we must apply its adjective only to measurement devices and not to a model. In the next chapter, we will discuss one of the most relied upon tools of science, hypothesis testing.